Okay, this lecture is over Module 12 of your curriculum. Module 11 was, of course, IP version 4 addressing. That's what we work with a lot. Module 12 is over IP version 6. So the first topic is, why should I take this module? Of course, this one's pretty simple to learn about. The topic of the chapter, which is IP version 6. What will you learn in this module? We'll talk about some problems with IP version 4 that led to IP version 6. We'll talk about how we represent IP version 6 addresses. We'll talk about the different types of IP version 6 addresses like we did with IP version 4 in the previous chapter. We'll talk about globally unique addresses and link local addresses. This is going to be similar to the IP address and MAC addresses in IP version 4. We'll talk about dynamic addressing for creating the global unicast addresses. We'll talk about dynamic addressing for the link local addresses. And we'll talk about multicast, and then we'll talk about subnetting, which is done way less often. It's kind of built into the IP version 6, if you will. So let's start talking about why do we need IP version 4. The most common is because we are running out or have run out of IP version 4 addresses. They may not all be in use, but they've all been divvied out. And that's kind of what this graphic here is showing you, is there used to be Internet, and it gave out all the IP addresses based in the United States. They decided there needed to be some competition, and as far as people who could sell different domains, and in the process they divvied out. For example, in North America we have Aaron, and then over here in Japan we have APNIC, which is Asia Pacific, which would include Australia. We have AFRINIC, which is Africa. So we have different places that IANA, Internet Assigned Numbers Association, gave out to portions of the world. And as we see, everybody has, quote, run out of IP addresses, with the exception of Africa, but during the year 2020, this year they're anticipating running out. So that means they have assigned them to registrars or organizations within their responsibility. So we are running out or have run out of IP addresses. Back when the internet was created in 1969, in 1969 there were 4 hosts on the internet. A year later, I think there were 7. A year after that, there were like 12. So they could never comprehend of using 4 billion IP addresses. But the computers become more and more popular. People can get internet at home, which you couldn't do till the late 80s, early 90s. And this thing called Internet of Things that they talk about down here is also caused some of this. Internet of Things is basically more and more things having IP addresses. Sensors hanging in trees in the forest to measure forest fires. Your TV has internet connections, and you typically have multiple TVs. Your DVR has an internet connection. Your car may have an internet connection. Your watch, your phone may have an IP address internet connection. So that's why we are running out of IP addresses. So there was an IP version 5. It primarily dealt with quality of service, which we've talked about. However, it never really went, quote, into production. So then they came out with IPv6, which is being used and is considered the wave of the future. The next section is on coexistence. And basically what that means is it wouldn't be really possible to say, okay, on date X, we're going to, quote, turn the internet off. Yes, all of it. And then everybody would need to install IPv6 capable hardware and software. And then you might say, okay, 24 hours after we turned it off, we're going to turn it on again. No more IP version 4, only IP version 6. Well, you can't really do that on a global scale. So what they did is they came up with ways that IP version 4 and IP version 6 could coexist. So basically you have something called dual stack, which almost all machines come with this turned on, which basically means IP version 4 and IP version 6 can coexist on the same network. And in some cases you'll have a computer that has both IP version 4 and IP version 6 running. So they can coexist. Now, if you don't have dual stack routers, which is a common problem, then you have to resort to something called tunneling, which is basically if between some routers, for example, they're showing here, you only support IP version 4, then your router can read IP version 6 and then encapsulate that into an IP version 4 packet, send it across the tunnel to another dual stack router who can then decapsulate that packet and pull the IP6 packet out of the IP version 4 packet and send that out on the IP version 6 network. And then finally, translation. We've talked about NAT. We've talked about it primarily for converting between private and public IP addresses. You can basically NAT or translate between IP version 6 and IP version 4. So I don't have any hard enough facts numbers on this, but I assume that tunneling is probably the most common thing that is being used at this point in time. So 12.1.3 is a check your understanding on why we have IP version 4 basically, or I'm sorry, IP version 6. So you can do that on your own. Okay, moving on to 12.2, IP version 6 address representation. So what we're going to equate this to, or similarities to, is an IP version 4. We have 32-bit IP numbers. That's 4 bytes. We convert each byte to its decimal equivalent and put a period between them and call it decimal dotted notation. So that is what the IP version 4 address format is. We've talked about this before, but IP version 6 addresses have 128 bits. So instead of doing decimal dotted notation, they take 16-bit hextets or segments, so basically 2 bytes, and convert that to the hexadecimal equivalent, and then put colons between them. So it would be hexadecimal number, actually 4 hexadecimal numbers, or hexadecimal digits, colon 4 hex digits, colon 4 hex digits. That repeated 16 times is how that would be represented. So what they're calling preferred format is the complete IP version 6 address with all 4 hex digits shown with leading zeros. For example, there are segments in here which are 0000. We'll talk about how we can deal with those later. But you know, :0 is one way to do that, and you just know you have to pad out. So the preferred format again is no shortcuts basically. Now, as far as the shortcuts, or what they're calling rules, the one I just alluded to was omitting leading zeros. So we can, as we've done here, get rid of these leading zeros, which makes the number a little shorter. And again, you just know that, oh, this is supposed to be 4 hex digits, so it would be 4 zeros here. So this is showing you the preferred format of some IP version 6 addresses, and then applying rule 1, which is eliminating leading zeros. So there's a whole bunch of those. The next rule, also ultimately related to zeros, is called the double colon. If you have a series of hextets that are contiguous, that are 0 in value, you can just eliminate all those and put 2 colons. And basically what the 2 colons mean, for example, if we look at this first segment down here, is it would be 2001 : db8 : 0 : 1111 : 200. So when we kind of compress this down and put all this together, the : basically means put however many zeros you need here so that this would expand out to 128 bits. Now then, you can only use this shortcut once. So here we had 0000000, and here we have 000000000. So we took the longest one. It doesn't really matter which one we do, but we can only do it once. So we took the longest one and put : here on the end, which means this is what we have. And once we get to this point, we just put our however many zeros, in this case 12, hex zeros, so that this expands out to 128 bits in length. So there's a bunch of examples of doing that. 1224 is an activity so that you can go through, take IP version 6 address in preferred format. You can omit the leading zeros, and then you can compress it down. And you can check your answer, or most of the time it says new problem, I think, but you know, in this case it's next, to take you to the next IP version 6 address that you're going to be working with. Okay, address types. There are different ways to look at this, just like there were with IP version 4. The first way in IP version 4 was that we had unicast, multicast, and broadcast. In IP version 6, we have unicast. It's the exact same thing, a one-to-one communications with a single IP address. We do have multicast, which is a multiple destination to anybody that is in the same or the specified multicast group. And in the case of broadcast, it was going to any device on local area network. In the case of IP version 6, you can have multiple devices on the network that have the same anycast address. And so what you're doing is you're basically broadcasting to any machine that has the specified anycast address. And they note real quick that this is beyond the scope of Cisco 1. Now then, it says IP4 does not IP version 6 doesn't specifically have a broadcast address. However, there is an all nodes multicast, which basically gives you a broadcast on the local area network. The next section talks about the IP version 6 prefix length. Basically, we take the IP address, we divide it in half. The first 64 bits are referred to as the prefix, and then the last 64 are the interface ID. So there are lots and lots and lots of networks or IP addresses. I can't remember if we talked about this before or not, but your book likes to say there are as many IPv6 addresses as they are a grain of sand on Earth. That didn't mean a whole lot to me, so I went out and did some looking, and basically if you took every square meter of Earth, water or land, we could put 600 million billion IP addresses in each square meter. So that's hard to imagine. That's probably way more IP addresses than there are molecules or atoms within that square meter. So we have lots and lots and lots. Talking about unicast addresses, there are different types we're going to talk about in upcoming sections, but we have global unicast, which is like an IP version 4 public address. We have link local addresses, which are going to perform the same function as a MAC address and does an IP version 4. We have a loopback address, one of the shorter IPs in IP version 6, which is : 1. There's only one IP address, : that's shorter. An unspecified address, they have a mistake here. This should really be : 0 or just : so this is a mistake in the curriculum. Unique local is the same as an IP version 4 address, and then you can have invented IP version 4, which basically, for example, I don't see they have an example here, but let's say you had an IP version 4 address on a device which was 192.0.2.33. What you would do is you would convert that to 64:FF9B : and then you would use the same values, : 192:0:2:233. Of course, those would be then in hex, but that's the IP address basically being the last 4 hex tets. Okay, so a unique local address, they're used for like IP version 4 addresses, but there are so many global unicast addresses, which are like public IPs, that these are not really being used yet. The IP version 6 globally unique address, again, this is the IP version 6 equivalent of an IP version 4 public address. They all start with 001. So these are 2001:D8/32. That one is reserved for documentation. But anything else that starts with 001 is a globally unique address, and again is basically a public IP address. Oftentimes what happens is the subnetting you do is kind of fixed. That is, you take 48 bits and say that's the global routing prefix, and then you have 16 bits for your subnet ID. So it's kind of like you're permanently borrowing 16 bits. And, 2 to the 16 is a relatively large number of subnets for you to use. within your organization. Okay, so 12.3.8 is talking a little bit more about globally unique identifiers. Sorry, it's 12.3.6. In that you have the subnet ID. So basically, what that'll do is if you did a /32 global routing prefix and used a 32-bit subnet ID, you would have 4.3 billion subnets, each with 18 quintillion devices per subnet. So like I said, these numbers are kind of crazy big when we're talking about IP version 6. And of course, the interface ID would basically be what we call the host bits in IP version 4. The link local address is basically the equivalent of a MAC address. In IP version 4, of course, an IP address is 32 bits. The MAC is 48. Since the link local address is an IP version 6 address, it also has 128. So basically, we have so many IP addresses that we can say, okay, these are global. We've only given out a small portion of those so far. These are for local network, and we've only given out a small number so far. So just like a MAC address, a link local address is non-routable. That means it will not pass through the router. Whereas if we have a globally unique address, which is the same as a public address in IP version 4, it is routable and would pass through the routers. Here it's just showing that routers use link local addresses because they're only talking to their neighbors to try to do something like neighbor discovery protocol. These addresses, just like IP version 4, can be statically assigned or hard-coded, or you can get them dynamically. There's a couple of ways to get that. One of those is to use DHCP version 6, but there's another way we'll talk about in a moment that address may be created dynamically. So 12.3.8 is a check your understanding on IP version 6 address types. So you can do that on your own. Okay, here we're talking about static configuration of the globally unique address. So that is basically hard coding. Here we have a topology. Looks like topologies we've worked with before. The only difference is the network numbers are shown as /64 IP version 6 addresses. So they are much bigger. If we log into a router and we go to the interface, instead of IP address to set the IP version 4 address, we would use IP version 6 address. The other difference is in IP version 4, we have the IP address and the subnet mask. In the case of IP version 6 configuration, we have the IP version 6 address and then the / prefix to basically tell us that this is divided in the middle, /64. So there's 64 host bits. And then the no shutdown brings up the interface. So this is how we would configure a router. On a Windows host, when we go in, we have normally gone to the IP version 4 TCP/IP properties. In this case, we would go to the TCP/IP version 6 properties, and we would give the IP address, the subnet prefix length, which again most of the time is going to be 64, and then we're going to give the default gateway, which is usually, it was a little misleading on this previous topology. they put ::1, which looks like localhost. But just like we did before, we're taking the network number and putting ::1 on the end. So they're basically using the first address in the subnet, which is often what we were doing in IP version 4. As far as the link local address, you go in and you configure the address, and instead of giving a / prefix length, you say link-local, so that it knows it's basically the MAC address equivalent for IVP version 6, in this case on router 1. So this is a syntax checker exercise. I think it's been a little while since we have seen this, but you can do this on your own. Again, it's where it tells you some information and then says, okay, go in and issue the iOS commands. So you can either do that, it'll tell you whether you're correct, or you can say show me, which shows you step by step, or you can click show all, which is going to tell you every single command that you would need to issue to accomplish all the steps outlined up here at the start. Okay, 12.5.1 is talking about dynamic addressing for IP version 6, globally unique addresses. We do have ICMP, which is Internet Command Message Protocol. We've most commonly talked about that in the context of ping and traceroute so far. But in the case of IP version 6, we also have router solicitation and router advertisement. So basically what happens is a host who is trying to figure out its address will send out a router solicitation. The router will find that. It will send back a router advertisement, which will have IP information that it can use. Basically, it takes the network prefix and the prefix link from the router, which is the default gateway, and then builds an IP address out of it. So that's one way you can do that. The other way that's referred to as SLAAC, Stateless Address Auto Configuration. So it gets that. You can talk to a DHCP version 6 server, which basically says, yeah, I got some information from the router, but I need some more information from you. Or you can use stateful DHCP version 6, where you simply talk to the DHCP version 6 server, and it gives you all the information that you need. So that would be the most similar to the DHCP for IP version 4 that we've talked about. So here they're showing where we're using stateless auto address configuration from the router. It sends out a solicitation. The router sends an advertisement. We then take the prefix and the prefix length from the router, and then we either generate a 64-bit random number, or we use EUI 64, which we'll talk about in a little bit. But basically, this is based upon the actual MAC address of the hardware. In the case of where we're using the stateless and stateless DHCP, basically what happens is the PC sends out the router solicitation to all IP version 6 routers. The router sends back the information. It basically says this is your prefix, this is your prefix length and default gateway, but you will need to get any other DNS information from the DHCP server. And so what happens is, in that case, the PC then sends the solicitation message to all DHCP version 6 servers, and it needs other information from the DHCP server, and then the DHCP server will supply that information back to the PC. That part's not shown here. In the case of just using stateful DHCP, it will go out, it will send out a router solicitation, it'll get a router advertisement back, but the PC will then gather all of its information that it needs from the DHCP version 6 server. The reason we still talk to the router is noted down here. That's the only way to get the default gateway address. So that does come from the router. Everything else comes from the DHCP server. Back to the interface ID. Randomly generated is pretty obvious. It just randomly generates a 64-bit number and crams it into the interface ID portion of the IP address and uses that. If we're using the EUI, basically the hardware still has a 48-bit MAC address, which is shown here. We split it in half. We put the OUI, the Organizationally Unique Identifier, at the first of the IP version 6 IP address. We take the last 24 bits and put it at the end, and then what we do is we stick FFFE in the middle of that. So it becomes, this is a 64-bit interface ID, so it becomes, that's how you generate it. So since the MAC address is supposed to be unique, then this IP version 6 address that you created should be unique as well. And also, since it's tied to the MAC address, it'll be a little easier to kind of check and see if things are working correctly. Down here, we're in an NMS-DOS command prompt. We did ipconfig. So you will see here that this address has FFFE in the middle. So it doesn't actually show us the MAC address, but we know that we take 24 bits this way, the 24 bits this way, put them together, and that would be the MAC address of the machine. Now down here, our link local address does not have FFFE in it, so we know that the last half of this was a randomly generated address. So 1258 is a check your understanding on dynamic addressing for globally unique addresses in IP version 6. You can do that on your own. Okay, link local addresses. So they're going to start with FE80, and then their ID interface is going to be either randomly generated or using the EUI64 process that we just talked about. So on Windows, we have the link local address shown. Again, this is kind of like the MAC address. It has FFFE in the middle, so we know it was generated from the MAC address, as well as its IP version 6 global unique address was also created using the EUI64. In the case of random, we go through and notice that the end of these are the same. So basically, the IP version 6 address and the link local address end with the same value. However, what they start with is different, so that we know we either have a globally unique or a link local address based upon the first hextet. 12.6.3 is showing you how you would see dynamic link local addresses on Cisco routers. So you would use show interface brief using IP version 6 instead of just IP. And you can see these addresses again. There's the FFFE, FFFE, FFFE. So all these were generated using the EUI64 process. 12.6.4 is talking about verifying IP address configuration. We would be doing this on router 1. So what happens is if we do show IP version 6 interface brief, we see something very similar with what we saw, as well as an indication as to whether a particular link is up or down. If we want to look at the routing tables, we would do show IP version 6 route, and we would see all of our connected and local interfaces as well as their IP address. And then, so that's verifying things are set correctly. If we want to verify they're actually working, then we would use ping just like we would, however, giving an IP version 6 address instead of an IP version 4 address. 12.6.5 is a syntax checker to make sure you understand the commands and concepts that we just talked about. Of course, you can do that on your own. 12.6.6 is a packet tracer activity that allows you to go through and configure addresses and then test and verify network connectivity. So I will be assigning that, so watch for that to appear in Blackboard. So we've talked about globally unique addresses, we've talked about link local addresses. We're now going to talk about multicast addresses. Multicast is very similar. We have an IP range that is for IP version 4 multicast. In IP version 6, FF00/8, so anything that starts with 8 ones basically, is a multicast address. Now then, we have well-known addresses and solicited node addresses. So we actually have kind of more clarification or division of multicast addresses. So FF02 is an all nodes multicast, so that's the thing we talked about earlier that's similar to a broadcast address in IP version 4. If we do FF02::2, that is an all routers multicast, so we can send a message that will go to all the routers. So those are two special ones. In the case of solicited node, we basically have a topology here. If we click on this little icon and kind of expand that, I do that because it's kind of hard to read. Solicited node multicast is like a normal multicast. If you send it out, this host down at the bottom basically says, you know, this multicast is for me because I'm in the multicast destination group. These two PCs are saying it is not for me. So we may not have used this symbol before, but this is basically expand and minimize a graphic. And like I said, the main reason I did that is because the shading they used it made it virtually impossible to read. 12.7.4 is a lab on identifying the different types of IP version 6 addresses. I will be assigning this, so watch for it to appear in Blackboard. Next, we're talking about subnetting. We can subnet, but with 16 bits, we have 65,536 networks. Each can have 18 quintillion hosts on them. So, you know, very rarely, if ever, are we going to need more than 65,000 subnets. Or more than 18 quintillion hosts. But like I said, if we do need more subnets, we can expand the subnet ID to be more. The previous example we saw was 32 and 32, for example. Here's a common way to subnet. If you have 16-bit subnet ID, that's 4 hex digits. So usually you just count like we do before, except you would count in hex. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc. And you would go all the way down till you had the 65,534th subnet, which would be actually it'd be 35th. Because we started at 0, which would be FFFF. So you just basically create huge subnets. Now, here we are, 50 years after IP version 4 came out, and we were saying, oh, they were super, super wasteful. MIT grabbed 16 million IP addresses, and they're probably not even using a million. They wasted 15 million. So here who knows, at some point in the future they'll be going, oh, those crazy people in, the early 2000s were wasting quintillions of subnets because of the way they subnetted. But just like they didn't see a point in time in the 70s when we would run out of IP version 4 addresses, this is crazy, 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 crazy big. So it'll probably be a long, long time before this causes any problem. I think with the fact of the global unique addresses they've given out now, they've given out less than 2% of the IP version 6 addresses, and that covers lots of different things. So here they're doing an example topology using the subnetting we did before. So here's subnet 1, subnet 2, subnet 3, subnet 4, and subnet 5. So don't forget there is a network between routers, even though that you only need 2 IP addresses. This is showing how to configure this. Basically, you're giving the first address, ::1, in the subnet to be the address of the interface on the router. So gig 000, gig 001, and the serial interface 010 on the router and iOS. 12.8.5 is a check your understanding on subnetting. You can do that on your own. And if we move to the module practice and quiz, the first thing we see is a packet tracer activity, which is implement an IP version 6 address scheme. So you go through, fill out a couple of addressing tables, and then actually configure and test the interoperability between the devices in the topology. I will be assigning that, so watch for that to appear in Blackboard. That is followed by a lab entitled Configuring IP version 6 Addresses on Network Devices. This is basically exactly the same thing as 12.9.1 Packet Tracer. However, if we were in the classroom doing this on real equipment, we would do the lab instead of the Packet Tracer equivalent. So, that finishes up Chapter 12 on IP version 6 addresses. What did I learn in this module? You can read through this on your own. Chapter 12 was probably a little shorter than normal chapter, but there's still a lot of information that we learn. This seems to go on and on and on. And then finally, you have the module quiz for Module 12, which was on IP version 6 addressing. So that finishes up Module 12 of the curriculum.